Alright, 5, 4, 3, 2, 1. Okay, so the reason I had you do this one, and some of my people in honors can probably remember me saying this. One, the more times you see something, your brain likes to see things like 7 times in various ways via, let's say FRQs, labs, interacting via online simulations, conversing and tutoring with others. But not only does the brain kind of look at things many ways and it's just kind of bring it into a really simplistic manner for like accessing in your brain, it also, like, if you read something, you only remember like 10% of it. If you speak it, it's like maybe 20 or 30% of it. But if you teach something to somebody and like truly verbalize the connections, you remember 90% of it. So I want you to like try to talk it out first, and that's why I have you guys tutor, right? It's not just because I'm like they need 10 hours of interacting with honors time, right? It's because you need to like learn how to teach the content so it really goes super solid in your brain. Got it? Okay. So I'm just going to hit the key points on these. I have typed up all the FRQ explanations because most of this is not math, right? So I'm going to use this. I'll just leave it there for a second, but let's hit the highlights, okay? So I'm going to ask for your help here. Electron configurations, I'm not going over. You got it? The last was 3p6 or 3s2, and then argon was 3p6. And then tell me some key points for why the values of the first, so B was kind of a two-part question, why the values of the first and second ionization energies of magnesium are lower than argon, and then the third ionization energy for magnesium is much larger than the third ionization energy for argon. Fatima, keywords.
I said the second ionization energy for magnesium is lower because you're removing the valence electrons and there's only 2, so it's easier to take them off.
So you just say that. What one of the valence electrons are? So that's the configuration, right? You need to mention this like the third energy level, or the third S, or 3s orbital. Okay. Okay.
And for argon, which is they don't want to be taken off because it's a noble gas, so it will lose its octet and become less stable.
Okay, raise your hand if you said something like that too. Alright, so you probably wouldn't get your credit because we cannot personify our atoms. They don't desire things like, wait, that's how we speak at them sometimes because it just makes sense to us. We're like, oh, it wants octet, it's to get octet. But we need to mention it more along the lines of stability, low energy, and that's going to be your points that you have to mention and get valid points for it. So argon is farther to the right on the periodic table, right? So what else does that mean for us? Higher depth. If you write the word or the abbreviation depth, like you want to use it maybe 4 times through a problem or an answer, just abbreviate it at the top of your FRQ sheet, and then you can use it. If you've never defined your abbreviation, they'll probably pick up what ZEP is, but that's a very common term. But if you're going to do something like TDF, thermodynamically favorable, they may or may not give you credit because you need to define it first. Okay? So, keep going. Please, tell me about argon and why it's, was it the third ionization energy smaller? So why is it going to require a lot more energy? Okay, so can we condense how we say that? The energy level is closer to the nucleus, therefore it's more attracted to the nucleus. What's better? Like shrink that down. JT.
They're undergoing nuclear penetration.
If it's S, yes. But if it's P, potentially no. But give me, there's a 2-word phrase. Coulombic attraction. You could say whatever electrons you're speaking of have stronger Coulombic attraction. Because it's in the second energy level. Like, you definitely should mention the second energy level still, that you can really, narrow down what you need to say. All right, and then, so let me tell you the key parts here. My computer shut down when I was editing this, but that's okay. Anyway, first and second ionization energy are lower due to the lower Coulombic attraction between the nucleus and the 3s valence shell, and that's just because you have less protons, lower nuclear effective charge. Comparatively, argon has a higher first and second IE due to the increased ZEF, which increases Coulombic attraction between 3p and the nucleus. And then, like you said, second energy level for the 3s orbital. For the 3s second energy level, greater Coulombic attraction due to it being closer to the nucleus. So if you can try to minimize and say Coulombic attraction, you mention a whole lot of things at once when you say that. If you're saying closer, you're saying more protons, there's a lot of things that can play into that. All right, so give me some key points on C. If a sample of argon in one container and a sample of magnesium in another container, each heated and formed gases passed over, what will be formed, if any? Carrington, give me a piece of that.
I said that magnesium chloride will be formed because argon already has a full octet.
When you say magnesium chloride, did you write out?
MgCl2.
Okay, MgCl2, so do you write that out?
And then I said argon has a full octet and will suddenly react to that magnesium once it becomes stable by accepting or by giving its electrons to its 2 chloride.
Okay, so it will bond with 2 chlorides by donation of 2 valence electrons in its 3s shell, something like that. And argon will not bond because it doesn't have any unfilled orbitals, something like that. Because argon is full octet, so it will not bond, so it doesn't have any unfilled orbitals. Something like that would indicate you referencing back to the electron configurations. Because you'll notice in part B and C, it kind of said reference back to part A, which is, part of the explanation. And then element Q has the following first 3 energy level or ionization energies. Drew, what you got?
UCl because that's one valence electron because the ionization energy jumps after the first ionization to a really high on the side.
Good. So we're mentioning the relative difference between the IE1 and then IE2. So first ionization energy is relatively low compared to 2 and 3. So this element must only contain 1 valence electron, making the QCl compound. All right. And then some of 87 overlap with the magnesium side of 82, but let's just chat about some of the others. The first one was like found that question. Within a family, alkali metals ionic radius increases as atomic number increases. What do you think, Megan?
Well, for the family, the alkali metals, you're not going across the period because it says it within the family. So you go down. And when you go down the family, you're adding more electron shells, so it should increase.
Okay, so you can simply mention the energy levels are being built around the nucleus, greater principal quantum numbers, which would naturally make that bigger, and you can also mention electron shielding because they kind of go hand in hand. The next one was regarding chlorine and chloride. I told you the angstroms. What are angstroms again? Anybody remember the symbol for angstrom? A with a little knot on the top. 10 to the 10th angstrom, so 10 billion angstroms equals 1 meter. It's just a unit of length, that's it. Just a unit of length. That's our unit for length. All right, so why is chloride larger than chlorine, Gigi?
I feel like the chlorine ion has one more electron, so it gets larger due to the electronization.
Okay, in the outside cloud. So if you want to say something, I'm just going to add on a word to that. If you add an electron to the electron cloud, electron-electron repulsion increases, which causes the cloud to expand, which is you trying to say it's larger. You could also mention the proton to electron ratio to say that the protons cannot effectively attract that last electron, which makes it relatively large compared to the other. And then C, aluminum has a lower IE than magnesium for its first ionization energy. What do you think, Darcy?
I'm actually a bit confused by this one, but according to what I said was that as you go across a period due to strong attraction between the protons and the valence electrons, that it actually...
So the trend looks like aluminum should have a higher ZEF and a higher IE, but remember this is our exception group. So 3A is an exception group. Give me a keyword. Come here, your table, give me a keyword. Okay, hold on. Give me a keyword on this one. Maybe like why does, in this case, like when we go from group 2A to group 3A, why is the ionization energy actually decreasing or lower? A lot of the filled and the half-filled stuff doesn't really justify our answers. It just kind of correlates. Cassie's area?
For aluminum, it has more electrons than some bubble, which doesn't go through the
Therefore, it has a
lower ionization energy.
good. You're good. Okay. So basically, you have to say something about nuclear penetration, which is the 3s electrons are more tightly held to the nucleus due to nuclear penetration, whereas the third 3p sublevel is not undergoing nuclear penetration. Therefore, it's going to be it will have a lower, i.e., lower ionization energy. You can also mention Coulombic attraction there. Okay, so let's just halt on that for a minute because I think the other one relates back to the other one we did. And then there's two more things I want to do before you guys start a video. Pull up your I gotta do notes. I didn't get to do these yesterday because we were busy. I only have about 4 slides of notes. So Roland, ready? So again, we see Coulomb's law. I'm just going to apply this in a slightly different manner. So basically, we're going to just talk about lattice energy, which when you hear lattice, what do you think? Lattice or lattice, yep. What do you think about? A crystalline structure. All right, so here's my lattice structure. We have a series of positives and negatives all in a lattice, which is an organized crystal. But there's a reason they are stuck together. There's a reason why they're solid at room temperature. It's because of Coulombic attraction. So we know that the magnitude of the charges, so Q1 and Q2, are going to be increasing the force of attraction. And if you have a large magnitude, what's magnitude mean? Number, right? So like large number, a large strength of attraction, it's going to be directly proportional to the force. This is of course regarding attraction. For now. And then the distance that separates those two charges, if the distance grows, the force goes down. If the distance is compressed or there's a little small distance between the two, the force goes up. So using the words directly proportional and inversely proportional might help you there. So if we're talking about lattice energy, which has a very specific definition, it's the energy it takes to break a crystalline structure. So in terms of breaking energy it takes to break an ionic or a lattice structure, do you think that energy would be endo or exo? I hear some questionable answers, like you're questioning yourself. Confidently? Endothermic. Okay, so remember the karate chop, right? Bonds. This is an ionic bond. But the bonds, anytime you break bonds, you're going to have to put energy into that process. So these are going to be endo values every single time. So because the force of attraction is strong, you have to put energy in to break up ionic attractions. So the force of attraction that we're talking about here is actually lattice energy. It's related to the strength of attraction of an ionic species. So this can be lattice energy as well. I'm just like interchanging that. So if you have ions that are +1 and -1 in charge, their magnitude of attraction is not too great. It's just 1. But if you have 2 ions that are 3+ and 3- in charge, they have a cumulative, what's 3 times 3? 9 magnitude. So it's a very, very large force of attraction. So therefore, this ionic compound would have a much, 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 much larger lattice energy. So somebody give me a 3+, 3- ionic structure. Say again? Aluminum what? Well, I know that's 3 plus. Give me the whole ionic structure. That's a 3 plus and a 3 minus. Say again? Nitride. That's it, aluminum nitride. Al3 plus and 3 minus crisscross, they're gone. That has a really strong lattice energy. Give me a 2 plus and 2 minus. Magnesium who? Oxide, okay. A little bit less than the aluminum nitride. And then give me a 1 plus 1 minus. I knew you'd say same, sorry. Okay, so 1 plus 1 minus. So as you can, you can easily tell the charges, and you can easily tell it's going to have a higher lattice energy. So that's going to regard the magnitude. These are the Q's, Q1 times Q2. And then the ionic radius, which is now what we know a little bit more about on atomic radius, that's going to play into the distance side of things. So really, really, really big atoms, or ions, let's say these two, the nuclide, meaning the internuclear distance, is going to be relatively large. So what happens to the force of attraction with this guy? It's going to go down because the distance is large. But if I have a compound that has two relatively small ions, their internuclear distance is not so great, so it's going to have a stronger attraction. Because essentially what's happening is the nucleus is being attracted to the external electron cloud over here, and therefore it needs to be somewhat close. So this nucleus, you can tell the board is off, right? Oh, good. Okay. This nucleus is attracted to this electron cloud over here. So if they're too far away, the nuclear attraction is relatively low. So we're just applying Coulomb's law to lattice energy. That's the big topic for today. Can I move on? Yeah? Okay. So I want you to talk to the people next to you why these three highlighted element or compounds have the lattice energy they have. We'll try to include factors that we just discussed.
Yeah, so like think about like the two goes in one, and the other two or something is bigger than one.
All right, now let's write down these examples together, okay? So 3, 2, 1, back to me, okay? So I mentioned earlier the definition of lattice energy. I just did a really generic, like, hey, it's the energy to break up an ionic structure. This is the exact definition because it includes gaseous ions, just like in ionization energy and electron affinity. He was talking about a mole of gaseous ions or a mole of gaseous compound. That is the exact definition, so make sure you do include that. So, but I'm going to only compare two at a time because it's going to be easier to consider one factor at a time. So lithium fluoride versus lithium chloride. We notice they're within the Coulombic attraction, right? What two factors are we considering? Distance and charge. So we actually, I didn't tell you this, the Q times Q thing is called charge product. Does that make sense? Like in terms of what we're doing? What's product mean in math? Multiplication, right? Charge is being multiplied. Q1 times Q2. That's charge product. Okay, so what's the charge product differences between these two? They're the same. So they're +1 and -1 on both fronts. So there's no difference in charge product. So the magnitude of the charge product is the same. Therefore, we defer to what? Distance or radius, right? So lithium and lithium is the same. So we can't really identify differences there. But what's the size of fluoride versus chloride? Who's smaller? Fluoride because it has one less energy level, one less electron shell. Okay, so fluorine is smaller, therefore more or stronger stronger Coulombic attraction to lithium ion. Got it? And that's going to increase the lattice energy because the force of attraction is greater. All right, so then can you do this on your own? Because I did the first one, do the second example. Either, actually, no, let's keep this consistent. Compare magnesium chloride and lithium chloride and write down why the lattice energy is greater for this one. All right, Margaret's table, what you think?
We talked about the charge product
Okay.
first, and so lithium chloride would be just one because it's 1 plus and 1 minus.
Okay, so lithium chloride has a charge product of 1, and that's just absolute value. Okay.
And then I looked at magnesium chloride, and it had the 2 plus and the 1 minus, and so that would have a charge product of 2.
Okay, and then how do you relate that back to lattice energy?
So, the greater it means that there's a larger energy it takes to break the crystalline.
Because of the larger magnitude charge product. Yeah, so just pulling those together. Good. So basically, if you have a larger charge product, you have a greater force of attraction between your ions, and that's really, that's really the biggest factor. The distances are not going to make a true difference because think about how we calculate this, right? Going back here. If you have a 1 times a 1 or 2 times a 1, that basically doubles your force of attraction, right? That's a whole doubling effect. But if your distance is changing by 0.1 angstrom, meaning the difference between these two ions are minuscule, it's not going to change your distance squared factor by very much. So the most significant factor here is always charge product or magnitude of charges. This is an insignificant factor unless it does become significant for, like, example, in our first example over here, because the charge product is the same, so then we had to reference that. You could reference radius as well, but I think you'd be wasting your time. Okay? Yeah. Because it's going to influence one of those singular factors, like i.e. EA, radius, and or EN. But because we have a combination of factors here, this is a more significant mathematical relationship. Okay. All right. So then we're going to apply this to this situation. So what happens is you sometimes are going to be given a lot of pieces of a puzzle. So a lot of pieces of how do I find the lattice energy of sodium chloride, for example. And in this case, you're given the sublimation energy. What's sublimation? Solid to gas of sodium. You're given the BDE, bond dissociation energy, of diatomic chlorine to form singular monatomic chlorine, IE, ionization energy, EA, and what's HF? Formation, right? Definition of formation is formation of 1 mole of a solid product from its 2 elements in our elemental states, or in this case 2 elements, so you have their elemental states. So basically what we want to do is we want to solve for lattice energy, which is this the reaction representing lattice energy? Yes or no? So Taz says no. Give me why.
Well, it's not lattice energy because well, can we think about it for
Okay, JT?
Maybe gas.
Well, it's gaseous ions. Those are gases. Okay.
because it's going from gas to a solid, not solid to gas.
So it's forming the solid. We're not breaking the solid, right? The definition of lattice energy was the energy it takes to break a solid lattice structure into its 2 gaseous ions. Okay. So I'm going to say flip this, which would be us representing the lattice energy equation. But what we're going to do is Hess's law. Remember Hess's law where we had equations and you cross them out on left and right and then you just add them up? Yay, let's do that. Okay, so I'm going to do it over here so you guys can use the board. But if this is our target equation, sodium chloride solid yields sodium ion gas and chlorine ion gas. Okay, that's our target equation. And I want to know delta H LE. Think about how to get started. Okay, think first, and then I'm gonna butt in. Okay. All right, I'm going to scroll up just for a second so I need to tell you why we're doing this. There's a reason, not just for kicks and giggles. It's because lattice energy cannot be directly measured. So we can't just like, okay, break the atom apart. Oh, how much energy do they require? We can't directly measure that. So what we do is we think about how lattice energy would be achieved, which these are all known values. So then we artificially calculate lattice energy by way of indirect calculations. Okay, so we know we want NaCl yields NaCl solid yields sodium ion gas and chloride ion gas, right? So let's go. If I have this first equation, the sublimation one, is it okay as it is? Looking down here. Okay, we don't see any of that relevant, but let's keep going because if you look farther, where else do you see? So like we take sodium solid to make sodium gas, we definitely want to cancel out sodium gas next, right? Because it's not, neither of those are here. All right. So I see sodium gas down here, which is going to undergo ionization to make Na plus and an electron. Is that okay as is? See sodium ion gas? It is, right? So I'm going to take both of those. I'm going to process sodium all the way through. It's till the form that I prefer it in. So sodium solid sublimes to sodium gas. Sublimation energy of 109. Okay, thanks. And then, so now I want to, I do know that in the end I'm going to have to cancel out sodium chloride. Just hold off on that for just a hot second, okay? And then sodium gas needs to go ahead and get swiped out. So I'm going to jump to the third equation. Sodium gas yields what? Sodium ion, gaseous, and one electron, and that's delta H, i.e. of 496. Okay? All right, so I know I'm canceling those out because they are gone. And do I want to cancel this one? No, right? I'm going to put a little square around that to remind myself to not touch it. All right, so I've basically processed sodium as much as I can. I'm going to figure out how to cancel this other one and this electron in a moment because you'll notice they're not here. All right, so chlorine. Diatomic chlorine gas yields 2 chlorines. And then further down, I see chlorine gas, an electron, and then chloride. What's the big difference between these two so far? Okay, so I know diatomic and monatomic. What else? Okay, I see charges. Do I see anything? Look at the numbers, coefficients. So this one makes 2 monatomic chlorine atoms, and this one only has 1. So I need to figure out: do I want to multiply this one by 2, or do I want to multiply this one by half? By half, because you want that 1 electron to cancel with that 1 electron for 1, and then 2, you want this chloride as is. You don't want half a chloride because the answer over here only has 1 chloride. So let's take diatomic chlorine, go to 2 monatomic chlorines, and we're going to multiply that whole thing by half, and the bond dissociation energy by half as well. BDE is, thank you, this angle's not great. Okay, so remember, whatever you do to a reaction in thermochemistry or thermodynamics, you do the same things with delta H. K's are different, right? Who was it? Billion, right? K's are different, okay. That's good. I like half the class today, this one. All right, so now we're in chlorine monatomic. What do I need to do? Go to the ion, right? So I'm using EA. So now chlorine gas plus 1 electron yields chloride gas, and what cancels? Okay, so the monatomic chlorine gas, because that's half right there, and so that's going to equal to 1. And then this was negative 349 EA, okay? All right, so who else do I want to keep so far? Chloride ion, right? So keeping those. So check. I've got both of those handled. Now I need to figure out how to get this involved. What's next? So do what with this formation equation? Flip it, because I need sodium chloride on the left, and I need to cancel out sodium and half of a chloride, or a diatomic chlorine. So NaCl, solid, yields Na solid and half of a diatomic chlorine. And what do I do with the delta H? When you say flip it, you mean make it positive. Flip the sign, not flip the, don't invert the number. Positive 411. And sodium chloride stays, check. And sodium solid cancels left and right. Half of a diatomic chlorine cancels left and right. Let's get that energy. Calculator. What is it? 788.5 kilojoules. Okay. That is the answer, 788 kilojoules, right? So first of all, lattice energy, should it be endo or exo? Endo, it is endo, okay, so that's 1. And then let's go back and check ourselves. Sodium chloride. What? Look at us. We're awesome. Okay. Very good. So Hess's law, just a quick reminder on how to do that. Did you guys pick up a little bit of this? We will do another example of this next week. Okay. All right. So do me a favor, grab laptops. Okay. Grab laptops. Church break. Oh, I gotta show you one more slide. Dang it, forgot this last one. It's good. I'll just get logged on. Yeah, only if you're really fast. But you just promised really fast. Alright, get those babies logged on. Thank you.
Really go back more.
Alright, log on. Log on. Emily, log on. Oh, it's right. Okay, well maybe this is Alright, so let me tell you what you're doing next, okay? So basically what our next job is what we're supposed to do now is to investigate more about the atom and about the energy it takes to swipe electrons away. Necessarily, it's a new concept in AP chemistry that they asked us to teach, so to keep it as concise as I could and like directly related to everything College Board has given us to teach with, which is not very much, but they give us some stuff here. I tried to correlate a little video on PES, photoelectron spectroscopy, to resources that College Board has given that they say are very valuable. And every year so far, they've had a question like this on the exam. So it's related to binding energy, which is really no different than anything else we've learned. Binding energy is the energy of the attraction between an electron and the nucleus. So what electrons would have the highest binding energy? One's closest to the nucleus, right? So 1s, 2s, and then sequentially from there, right? 5p is going to have the farthest away from the nucleus, so therefore it's going to have the lowest binding energy. But that's really what we've already learned as ionization energy. It's just with ionization energy, we haven't really talked about taking internal electrons. We've been talking about taking valence, and then the next shell in, and then the next shell in, and the next shell in. So I'm not really using new terminology. I'm just elaborating on how we can talk about ionization energy. So this is related to photoelectron spectroscopy, PES, which puts out graphs like this, which talks about the binding energy the electron has to the nucleus, and then how many electrons are in those various shells or subshells or orbitals, which is what this is like intensity over here. So you're going to do a little bit of investigation. Go to edit puzzle for me. Please do not make a fifth login. I will tell you login if you need a login. Some of you guys are in the class like 2 or 3 times at this point. Okay? So there's some questions built into the video, and then I will tell you there's a activity that we'll do afterwards. So I will stop you like at the end of class to tell you about that, okay? So let me show you. It may work for me here. So when you start, it's going to look like this. I'm going to do a lot of drawings of peaks. So ensure that you are drawing those with me, answering the questions and finishing up, okay? So I'm going to give you about half an hour right now, and let's see where we are. And if you need some of those awesome headphones, they're underneath the table here. Okay, you're good. Use them underneath, behind that desire.